Hello, this is Santhiya Nithyanandan, and this is the first homework in the coursework EDG6370, and it's on the design of combinational logic designs using schematic entry and Verilog or VHDL using Intel Quartus Prime. So this is the schematic of the 1-bit full adder. I've used 2 XOR gate to generate the sum and 2 and 1 OR gate to generate the cout output. I'm making this as the top level entity and compiling this. The compilation process is done and the report is generated. Here the logic utilization in ALMs are 2, the total number of pins are 5, and also the total number of memory bits are generated. Now let me get into the resource utilization by entity, and the combinational ALUTs are 2 and the number of pins are 5. Let me open timing analyzer and I'm reporting the path. Here the critical path is from node C to node C out, and the delay here is 8.611. I'm closing this, getting back to project navigator, removing this .bdf file, and I'll be adding the VHDL and the test bench file. I'm setting this as top level entity, and this is the test bench file. Here are the test cases that I generated. Now let's compile this. The compilation process is done and the report is generated, and it's similar to that of the schematic files report. The ALUTs are 2 and the number of pins are 5. I'm again getting into the timing analyzer. Reporting path, and even this is similar. The critical path is from node C to node C out, and the delay is 8.611. Now let's simulate this. Let me compile the test bench file. Here I'm getting 0 error and 0 warning, so it's done. I'm simulating the test bench file. Adding all the waveforms, and I'm starting the simulation. Here is the output. Let's take a test case. Here the input A is 1, B is 0, and Cin is 1. So the sum is 0 and the cout is 1. So it's the 1-bit adder is working perfectly. I'm closing this and getting back here, removing both these files. And I'm adding the behavioral code of 4-bit. So this is the behavioral code of 4-bit full adder, and it's test bench. I'm setting this as top level entity and compiling this again. So the compilation is done and the report has been generated. So the number of ALMs here are 3 and the total number of pins are 5. Let me get into the resource utilization by entity, and the number of ALUTs here are 5 and the total number of pins are 14. Let's go into the timing analyzer. Report path. Here the critical path is from node C into node sum of 2, and the delay here is 9.642. I'm closing this window and I'm simulating this file. adding the test bench file. I'm getting 0 error and 0 warning. I'm simulating this. Adding the waveforms. So let's take a test case, say B is A and A is 1. So adding these two will be getting sum as B. So it's working as expected. Now let me add the same 4-bit but a structural code. And I'm removing these behavioral codes. Setting this as top level entirety and compiling it. So this is the structural code of a 4-bit full adder, and this is the test bench. So let's get back after the compilation is done. So the compilation is done and the report has been generated. The number of ALMs are 4 and the total number of pins are 14. Now let's get into the resource utilization by entity. Here the number of ALUTs are 6 and the total number of pins are 14. Getting into the timing analyzer. Here the critical path is from A of 1 to sum of 3 and the delay is 9.561. Let me close this and do the simulation. Let me add the test bench file. I'm getting 0 error and 0 warning. So yeah, this is the output. So let me take this test case and then analyze it. So the input here A is 1 and B is 2, so the sum output is 3. So the circuit is again working as expected. Let me close this. Now let's add 8-bit behavioral code and remove these two 4-bit structural codes. Let me make this as a top level entirety and simulate it. This is the 8-bit behavioral model code and this is the test bench. So yeah, now the compilation is done and the report is generated. Here the number of ALMs are 5 and the total number of pins are 26 and the ALUTs here are 9. So I'm getting into timing analyzer to report the critical path. The critical path here is from node A of 0 to node sum of 2 and the delay here is 19.659. I'm closing this and I'm simulating this 8-bit full adder. compiling the test bench, and here I get 0 error and 0 warning. I'm simulating this file. Add waves. So let me take this test case where the B is 30 and A is 9 and the output sum is 39. So again the code is working as expected. Let me close this, and I'm getting into add remove file. The same 8-bit code, I'm adding the structural model now. We already did the behavioral model. I'm removing the other two codes, setting this as top level entity again and running the code. So this is the 8-bit code of a structural model and this is the test bench. So the compilation process is going on. Let me get back. Here the compilation is done and the total number of pins are 26 and the logic utilization in ALMs are 9. So the combination ALUTs are 14. Let me get into timing analyzer to check the critical path. And the critical path here is from node A of 1 to node C out, and the delay here is 15.566. I'm running the simulation. Compiling the test bench code. I'm getting 0 error and 0 warnings. So I'll be simulating this. Adding all the waves. Let's take one test case where we are adding 15, that is the input of A, to the input of B, which is 2C. So we'll be getting 41 and the carry is has been taken to the next adder. So it's again working as expected. So let me close this, Vista, get back to Quartus Prime. Now let me add the 16-bit behavioral code. And I'm removing this 8-bit code, setting this as a top level entirety and starting the compiling process. So this is the 16-bit behavioral code and it's the test bench for that code. Here the total number of pins are 50 and the ALMs are 9 and the ALUTs are 17. So again getting into the timing analyzer to report the critical path. So now the critical path is from node A of 0 to sum of 6 and the delay is 16.174. Now let's go and simulate the 16-bit adder. Let me compile the test bench. And I'm getting 0 0 error and 0 warning. Let me simulate this. Add waves, and after running this, let's check one test case. Let me take this. Here the input of A is 0001 and the input for B is 0002. I'm getting the sum out as 0003, so the code is again working as expected. Let me close this, and for the same 16-bit, let me add the structural code now. And I'll remove the behavioral code, setting this as a top level entity and starting the compilation process. So this is the 16-bit code, the structural model, and this is the test bench for that. The compilation is completed and the total number of pins here are 50 and the number of ALMs are 19. So here the number of ALUTs are 31. Let me get into the timing analyzer. Report path, and here we'll be getting the critical path, which is from node Cn to node sum of 15, and the delay here is 20.886. Let me close this, go back to the Quartus Prime and run the simulation. Let me add the test bench code. I'm getting 0 error and 0 warning. Let me simulate this and add all the waves. And again, let's take a test case where the A is 0001, B is 0002. So the sum which we should be getting is 0003, and it's similar the case. So again, the RTL for 16-bit structural code is working perfectly. So here ends the first homework. Thank you.